Hello everyone, and welcome to Office Hours with the Meter Environment team. Today's session will focus on soil water potential, and we're shooting for about 45 minutes of Q&A with our experts Leo Rivera and Chris Chambers, whom I will introduce in just a moment. But before we start, one housekeeping item. If you're watching this video and you think of a question you'd like to ask our science experts, we encourage you to submit your question on our website at metergroup.com. And someone from our science and support team will get back to you with an answer via email. All right, with that out of the way, let's get started. Today, our panelists are application specialists Leo Rivera and Chris Chambers. Leo operates as a research scientist and director of science outreach here at Meter Group. He earned his undergraduate degree in agriculture systems management at Texas A&M University, where he also got his master's degree in soil science. There, he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in meters hydrology instrumentation, including the Saturo, Hyprop, and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. Chris Chambers operates as the Environment Support Manager and the Soil Moisture Sensor Product Manager here at Meter Group. He specializes in ecology and plant physiology and has over 12 years of experience helping researchers measure the soil-plant atmosphere continuum. So, thanks for joining us, guys.
Happy to be here.
Yep.
All right, let's get started taking questions. Our first question here is, for the TEROS-21 sensor, what is the measurement range that gives better precision? Does it require calibration or not?
Yeah. Do you want me to take that one first?
Yeah, go ahead.
Okay. So the TEROS-21 is a calibrated sensor in the range of about -5 kPa to -100 kPa. Within that range, we have really well-defined accuracy specs and understand the behavior of that sensor really well. And having said that, though, it does measure beyond that down to about -100,000 kPa. And that range of the measurement, we're continuing to work more on to better understand the actual performance of the measurement in that range.
Not necessarily to 100,000 kPa.
Not necessarily correct. Yeah. Ideally down to about at least down to permanent wilting point, and down in some applications down to about -4,000, -5,000 kPa. We want to really have that pretty well characterized so that way we can better inform that. But it isn't calibrated because it's nearly impossible to calibrate a sensor in that range without making a sensor that costs, thousands of dollars versus a couple $100. But we are learning more about it and diving into it, and we're seeing more publications come out too about the behavior of these sensors and other sensors in this range. And so I think there's more work out there that we're seeing that, but it's still beyond the calibrated range. It's more of a qualitative measurement.
And that's the trick, is when you get to that dry range, it's hard to know what the real matrix potential is.
Yep. So, but no, it does not require calibration because it is calibrated. So we take care of that for you.
All right. Next question. If the soil is dry, does this affect the suction measurements by the TEROS-21?
Not beyond just the actual physics of how water moves in really dry soils. So it will, the sensor is in equilibrium with the surrounding soil, and water will get pulled in and out of the sensor based on the suction of the surrounding soils.
Yep. No, that's absolutely right. It really just depends on water movement. The only situation where you might run into issues is in expansive soils where you could get shrinkage away from the sensor. But
and then all bets are off.
That's with any sensor, though. Once you lose contact with water potential measurements, especially with field sensors, is really highly dependent on good soil to sensor contact. And expansive soils cause issues with so many different measurements, and this one's also susceptible to those same issues.
Yep.
Unfortunately.
All right. Next one is asking, do you have any experience in measuring water potential in soilless media? What are the challenges? What is best? Tensiometers, TEROS-21, etc.
Yeah. And, I have my own personal experience with water potential in soilless media was heartbreaking. Because, I was thinking, I want Well, matrix potential is definitely the best way to go if you want to know the status of a water status of a plant. And I took my eyes off of the reading for like 10 minutes, and then the plant had gone and then the plant had wilted. 10 minutes is a bit of an exaggeration, but there's a couple things working against you here. There's your soil to sensor contact, or your soilless to sensor contact.
Yeah.
And there's the shape of your soil moisture retention curve. And that's the nature of a lot of soilless media, is that they hold water and then they hold water, but they can drain really quickly.
Yep.
So it's like you're driving over a cliff. If you're going to use matrix potential, you better know exactly where your refill points are.
Yeah, no, that's absolutely right. And really, when you think about most soilless media, the bulk of the water is held in the really wet range. And once you go beyond that, things change really quickly. Really quickly. And so when you think of your traditional ranges in soil that you're going to try to stay within, it's completely different in soilless media. You're typically not going to try to push soilless media past minus 30 kPa, really, because once you get to that point, then it really like Chris said, it drops off really fast. And there are other factors at play that actually impact the availability of water, like hydraulic conductivity. And we've seen this in other research where at points where you would expect plants to not be stressing, you're seeing stress. Say, for example, at minus 10 kPa, we've seen this in some materials. So your water potential ranges differ. And because of that, you're typically better served with something like a tensiometer in soilless media, because they give you more precision, and so it helps you understand those characteristics of the soilless media better, and especially because you're not going to want to try to push those medias very far.
And where you're used to watching matrix potential in, say, a mineral soil, you can watch it creep, and when it starts to dry down, you can kind of watch the projection, you know, and look forward, and it's like, well, a couple hours, this is going to hit my refill point, and so I can just chill out for a little bit, come back and check on the data later. Be careful doing that if you're in soilless media.
Yeah.
Okay, this next individual is asking, can you talk about conditions where you would see positive pressures in conditions that are less than saturated?
Yeah, that's a really good question. So there are a couple instances where you're going to see positive pore pressures, and it also is dependent on having the right tool to actually be able to make that measurement. Because if you're using something like a solid matrix sensor, like the TEROS-21, where you're using another measurement to relate and get that water potential, you're actually not going to see that. So you need something that's more of a direct measurement, like what you get with the tensiometer, where you can actually measure those positive pressures. And of course, for sure, you're going to see positive pore pressures in saturated conditions, but you can see that occur in less than saturated conditions if you have entrapped air, or if there's something physically imposing a positive pressure on the soil. So in many geotechnical applications, we see the other things that cause positive pore pressures, even though the soil isn't completely saturated. But there's a lot you have to understand about that, but the measurement of positive pore pressure is really important, especially in applications like slope stability and understanding the risk of slope failure.
Where it's going to be much more likely to slide if you've got that positive pressure.
Yeah, because the beautiful thing about negative or dry conditions, when the soil has a lower water potential, that water potential actually is something that helps increase the soil strength, because it's actually helping hold the soil particles together. But when conditions approach positive pore pressures and then become positive, then those equations completely change.
And that's where your tensiometer is going to be great, because that pressure transducer, the water column pulls on the transducer when it's really dry and you get tension. But it's just, you flip the sign in positive pore pressure. So you're exerting pressure on that pressure transducer instead of pulling on it.
Yeah.
This question is, how does or can organic matter content affect water potential? Is this something that could be calibrated to an existing water release curve?
Well, it definitely impacts it.
It definitely impacts it.
Yeah. I mean, we know that typically as you increase organic matter in soil, it increases the water holding capacity of the soil. And in turn, that means it's going to impact the soil moisture release curve. Now the challenge there is, and I think what this question is trying to pose is, can we determine what that change is going to be, maybe just based on the percent of organic matter increase?
Well, the nice thing is that the matrix potential, just by its nature, it doesn't matter.
Absolutely.
Minus 100 kPa is a minus 100 kPa, whether you have a high organic matter content or not.
Yeah.
So that's working in your favor. But as far as calibrating it, that's right. You were about to mention how you could use the soil water retention curve to look at a shift in the curve with organic matter. Yeah,
I think it's really hard to estimate exactly how it's going to affect it because there are other factors at play, of course, structure and other things. Mm-hmm. There are pedotransfer functions out there that people use to try and estimate these curves and what that would look like at different organic matter contents, but they're not 100% accurate. So if it's something you're really interested in understanding, the best thing to do is measure and take samples and measure those changes over time, or even better, have in situ measurements of both water content and water potential. And then you can actually monitor how that relationship is changing over time in the field.
Or if you're making a comparison to the effects of it, then sample, bring it back, put it on the high prop.
Yep,
and
exactly.
Yep.
A plant question for Chris Chambers. What is the relation between water potential and turgor of a plant?
Oh, fun. We're really getting into kind of the physiology here with this one. So, and this is going to depend a lot on plants. Basically, the turgor pressure is what gives a leaf or a non-woody plant its structure, right? It's what it allows it to stand up, change the leaf angle to track the sun or whatever. And that's going to be directly related to the water potential of the leaf. Now, this strays a little bit from our soil water potential because mostly we're looking at stem or leaf water potential for things like this, which, of course, are going to be dependent on soil potential to some extent. But basically, the point at which the potential at which you lose turgor is a pretty important physiological trait in a plant. And that's going to vary by species and it's going to be affected by environmental conditions. But basically, the turgor loss point is going to be where plants wilt and then lose a lot of function hydraulically.
And so and there's no real, I mean, and I'm going to ask this question because I'm the soils guy, not the plant guy. But, when we measure water potential in the soil, it is not a direct indicator of your plant turgor pressure and what that's going to be experiencing, right? Because there's so many other factors at play.
Exactly. There's a lot of different factors at play. And then when you get into plants with more sclerified tissue, then it gets harder to observe and relate that turgor loss point to the water potential.
Okay, here's a big one. How can we relate water potential with water content?
The soil moisture release curve.
All right, he's off.
Yep. So, I mean, this is a pretty common question and an important question to ask is how can we make that relationship? And of course, we have this wonderful thing called the soil moisture release curve. I think the more important part is how are we generating that relationship and how are we using it? Especially, and especially because we can make this relationship, but one of the challenges with trying to relate that in the field is we have hysteresis and we have other things at play that actually cause the soil to be on different scanning curves and things like that we don't have a lot of time to dive into. But a common tool is to make soil moisture release curves in the lab and then use that relationship to apply that to field and data in the field. Or people try and go the route where they model these relationships using the pedotransfer functions. And which isn't my favorite way to do it because of pedotransfer functions don't take into account all of the things that impact the soil moisture release curve in that relationship. But it's a way to go.
And it has a lot of value beyond just being able to transfer back and forth between water content and water potential.
Yep.
Because it's really, maybe fingerprint for your soil isn't quite the right term. But if you're characterizing soils and the soil is what is important to you and how water moves through your system, then that soil water retention curve is going to give you a lot of insight between different sites and different growing conditions. Yeah,
absolutely. I mean, it's soil moisture release curves are commonly used in vadose zone hydrology modeling to understand how water is going to move in soil and those types of things. So it's a really important curve to understand. And we're all familiar with the term Van Gunington parameters, which is just one of the equations that's used to fit this relationship. There are other tools that are also used for that. But it's a powerful thing to understand in many areas.
Okay, and a follow-up to that, or a secondary follow-along question. If you are co-locating water content, water potential sensors, how close can or should they be to each other?
Ooh, that's a great question.
Close enough that you're reading basically the same hydraulic conditions and soil and everything soil structure, right? Because they've got to be close enough to be measuring the same forces.
Yeah.
Far enough apart to not interfere with each other.
Yep, exactly.
So a few centimeters, basically, right?
Yeah,
it's going to be ideal.
Yeah, and we know. I mean, you want them as close as possible. We know that there's always a chance of some variability just due to finger flow and of water and soil, and just different things about spatial variability within the soil. But the closer, the better. And for the most part, that little bit of error that you're going to get from their slight difference in proximity to each other is going to be fine. Now, if you're dealing with transition horizons where you might have an irregular boundary, then you might want to be careful. Now, this is something, if you're not actually characterizing the soil, you're not going to know this, but you run the risk in some of those transitional horizons where you could wind up with textural discontinuities between the two spots. And so you do have to be a little careful, but this is not, I mean, it's not that common where you're going to run into a site where you're going to see that big of a difference. But if you have your sites characterized well enough, you'll know that you could run into something like that.
So basically find the measurement volume of your water content sensor and give a little bit of a healthy boundary beyond the most conservative limits of that, and you'll be in good shape.
Yeah. Next question, how do you determine the volume you are measuring?
For a water content sensor, that's really easy. We're emitting an electromagnetic field into the soil. But for a matrix potential sensor, all of which, to my knowledge, require equilibrium with the surrounding substrate, right?
Yeah.
Then, so how big, how representative is that? How far away from your sensor would you expect the matrix potential to differ?
Yeah, I think the nice thing about water potential, I mean, it's a very point measurement. Like it's whatever is in direct contact with the sensor is what you're measuring. But the beautiful thing about water potential is it's an energy state, and so it's always trying to come into equilibrium. And so it typically will represent a decent area around it. Now, as you go through like big changes in water potential or rapid changes in water potential, you might see some differences in areas that are further from the sensor or not as closer to the sensor than what you would see in maybe drying conditions where it's not transitioning as quickly. But it's not like water content where I think you can see bigger variability in water content than you would see in water potential because of the fact that it's an energy state. But it really depends. I think it really depends on the soil that you're working into.
Number one variable that's going to affect that.
Number one variable that's going to affect that, I think, is going to be
hydraulic conductivity, right?
Yeah, hydraulic conductivity. Yeah, and hydraulic conductivity and flashiness of the system. So, like, if you have a really rapid rainfall event, or if your soil is more prone to like finger flow and things like that, then, or if you have big macro pores, then I think you'll see bigger differences in smaller areas.
So really complex question that, we don't have all the answers to, but it's fun to delve into it.
Yeah.
And, as you get kind of related to finger flow, as you get drier, then, the path that it takes for water to move through the soil gets longer.
Yep.
So it's going to vary by condition and, fun question, but really, really tricky to fully get to the bottom of.
How can we calibrate or validate the tensiometer and make sure the sensor is working?
Yeah. It's really the bigger question is how can we validate the performance of the sensor in the field?
They don't drift very often, right?
They don't, depending on the pressure transducer that's being used, and the quality of the pressure sensor. So it also depends on where you're getting your tensiometer from and the quality of the transducer that they're using for the measurement. Most sensors, we don't see a lot of drift. So how do you validate that it's behaving in the field and is accurate? It's actually kind of hard to do in the field because you need something that you can apply in no suction.
That's right. You'd have to excavate it for one. But, it's fairly easy to a hanging water column with the length of your shaft and a 0 point for pure water. So it's not an insurmountable obstacle to validate it. And then a good test, more frequently we get the question of, is my tensiometer working? Right. It's not changing. What's going on? Has it cavitated? Has it got air entry? And so in that case, saturating it, saturate the tip and then let it dry out. If it's just drying in the air, especially on a hot day, it should respond really quickly.
Yep.
Okay. Here's a combo question here for the solid matrix sensor. What happens if the calibration is wrong? It's calibrated wrong. For instance, if the sensor gets changed from one soil to another, what do we need to do? Also, who calibrates the sensor? Is it meter group? Or can the user change the calibration based on needing to move the sensor?
Yeah.
All of our matrix potential sensors are calibrated, right?
They are all calibrated.
Every single one.
Every single one. We do not ship an uncalibrated. We better not be shipping an uncalibrated.
We're not supposed to ship an uncalibrated sensor.
An uncalibrated sensor. And the beautiful thing is the calibration is based on the properties of the sensor itself, not moving it from one soil type to another. So it's not something you really should ever have to worry about changing.
And if it's functioning properly, it doesn't drift.
Yeah.
The TEROS-21 is based on our water content sensing technology, and then we use the water retention curve to infer matrix potential from the known ceramic. And that just doesn't drift. So you don't have to worry about the calibration. I do want to circle back. Our Zentra software will tell you if it's not calibrated. So you can just not worry about that. Use a ZSC or a ZL6. And if there's a problem with the calibration, it will let you know. And then we'll give you a sheepish, very embarrassed replacement as soon as we possibly can. It hardly ever happens. Now, if the calibration is wrong, that's a little trickier.
Yeah. And that's one thing we work really hard to try and prevent. One of the things that we do when we calibrate our sensors is we then run them through a verification process where we're checking the calibration points that were input to the sensor to make sure that it's reading within the spec that we expect the sensor to read within. And then on top of that, we do monthly verification of sensors where we pull subsamples and check the performance of those sensors to make sure that they're also reading, that they continue to be within spec.
Independent quality check.
Yep. Yeah. And so it's not really something that we ever hoped that we ever expect to see. Now, crazy things happen, but it's not, especially with the solid matrix sensors, it's actually not something we've seen much of because the verification process does a pretty good job of checking sensors. And when they are out, they flag it, and then we go through and recalibrate it, or we don't ship that sensor out if it can't meet the spec.
Exactly.
Next question. The previous TEROS-21 Gen 1 10 kPa lower limit generally corresponds with the ceramic head air entry value. How close does this limit correspond with fully saturated conditions? Is there a benefit to reducing that 10 kPa lower limit to 0 kPa to better identify saturated conditions?
That is a really good question. And, when we first developed the TEROS-21 or the MPS-6 or the MPS-2 at the time, we actually had that same assumption that the limit was due to the air entry of the ceramic. And as we started diving into refining the electronics for the Gen 2, we learned that the limit was actually not the ceramic. It was the limit was the electronics did not have enough sensitivity to see changes in the ceramic in that range. Now we do know now that we've better refined that, we've learned that the air entry of the ceramic is somewhere around 3 to 5 kPa, depending on ceramic to ceramic variability. And if you look at our specs, you'll see that we spec from -5 to -100,000 kPa. And that's because we know that we can rely on the ceramic reaching air entry and responding at that point. But it really actually had to do with the electronics. And the really cool thing is when the sensor now goes on, that's on the drying curve when you're desaturating. But when it's wetting back up, it can actually detect changes all the way up to saturation. And so it might sit there for a little while after saturation before it reaches air entry, but we are able to actually better detect those ranges. And that's really the really cool things about the Gen 2 for the TEROS-21 and now the TEROS-22 as well.
But it can also be why your TEROS-21 might seem to linger at -0.1 kPa for a while on the drying curve.
Yep.
Because it really might not be able to distinguish between that really near zero matrix potential and 3 or 5 kPa.
Right. Yeah, and there are still definitely limits on what it can do in that range, but we've been able to improve that and better understand now the limitations there.
And if you really need to know what's happening in that range, you should be using a tensiometer.
Absolutely.
Okay, next question here. What factors affect soil water potential and how do they interact?
That is a really good question.
It's great. So this is where we need a board.
This is exactly where we need a board.
Don't have a board.
One day, Chris will have his board to write on.
Well, okay. Just to bring it home, how desperate we are for this, we're going to air dry. So we're going to have psi t over here, right?
Yep.
Okay. So you got to fact check me. You
Yep.
got to double check
I'm
my
listening.
math.
Yep.
Okay. And then psi t is going to equal, let's see, psi p.
Yep. Your pressure potential.
P.
Yep.
And then, wait, I always get the sign wrong here. Minus psi m.
Yep, your matrix potential. It's plus, yeah.
Plus.
So it's all additive because some of them are negative and then some are positive.
O. And then osmotic.
You're
and then
one.
there's one more.
Yep.
Psi g.
Yep, your gravitational potential. So you got your 4 main components of water potential, and then you have the 2 that are primarily dominant in unsaturated conditions, which are psi m, your matrix potential, and psi o, which is your osmotic potential. And so those are your factors that impact total water potential.
Total water potential.
But then if you dive even deeper and just to the matrix component of it, there are dozens of factors that impact matrix potential.
Right.
You have structure, you have obviously your particle size distribution, and you have bulk density, organic matter. Let's see, what am I missing? There's others. So, and I'm going to hit on pedotransfer functions one more time. So if you look at a traditional pedotransfer function, they're like what you see in Rosetta, there are a couple ways they'll break it down to get your retention curve. One is just purely based on the not the particle size distribution, but just on the texture. So you can say that you have a sand, and Rosetta will generate a soil moisture release curve for you. As you can imagine, it's not super accurate.
Now, how does this tie in with Dr. Liu's research with the VSA on specific surface area?
That is an even deeper dive.
Okay.
So, I think what Dr. Ning Liu has been diving into is really all the components of the curve, and like you deal with the capillary portion of it, and then you have the surface, the stuff that's bound to the surfaces of the particles themselves, and that's a deep one to dive into today. But just those pedotransfer functions can also break it down by particle size distribution or particle size distribution and bulk density, and as you add more factors, your pedotransfer functions get better. But that's the thing, is there are so many factors that impact your that relationship. And I'm probably like getting off way in the weeds here, but
the point is that there's various levels.
There are various levels.
So breaking down even your matrix potential, but the dominant force is going to vary depending on the conditions.
Yep.
Like drier than minus 30-ish kilopascals, the gravitational potential just kind of becomes insignificant in that, right? And then your matrix potential is your dominant force in water movement.
Yep.
In that soil.
Yep. Yeah.
So tell me about osmotic potential. I get confused on this one sometimes.
Yeah, I think osmotic potential really only so it has to do, really plays a role when you're dealing with semi-permeable membranes.
Mm-hmm.
So
any biology in the soil.
Exactly. So for water movement, osmotic potential doesn't really play a role. But for plant water uptake, it absolutely plays a role. And so you can see more stress induced. And so that's one of the things that salt does, is salt introduces stress, not just because it's there and it can damage the plants, but it also more tightly bounds the water to the plant.
Right.
So, and then pressure potential is only in saturated conditions, typically.
Right.
So,
yeah, we already covered that.
All right. This next question is, what are the implications of soil water potential for agricultural irrigation management?
So I love matrix potential in mineral soils for growing crops. And when we're talking with growers, part of this has been really good of a development over the past decade or so to get growers used to using water, soil moisture as an indicator on how their plants are doing. But it's also a little bit of a limitation because water content is much easier for people to understand. Yeah. Right. I'm gonna talk to Leo in terms of KPA if I know it, if we're talking about water status. But when I'm talking with someone on the street, it's gonna be percent water content, right? It's 35%, it's 15%. It's really easy for people to wrap their head around. But those numbers all mean something different in different soils. Yeah. And almost every agricultural operation has this soil type variability to deal with. Yep. And you can just cut straight through that with matrix potential. Yeah. And just look at the water status for that crop. And it doesn't matter whether it's a clay or a sand. It's minus 50 kilopascals is minus 50 kilopascals. Yeah. So that's where matrix potential is really so much more powerful than water content. But it's a lot more difficult to interpret. Yeah. And to explain to someone how to interpret. Yeah.
Yeah, it's true. I mean, unfortunately, water potential is one of the hardest subjects to teach in soil science. And you're teaching that to soil scientists. So imagine trying to teach it to somebody who is not a soil scientist. It's even harder. And so it's really hard to explain that. Now, the really cool thing, though, is there are these, we have pretty well-defined ranges that we know many different types of plants are happy in.
You can almost always find a starting point in the literature.
Yeah, exactly. And so if you have that measurement of matrix potential, you can always go back and say, okay, am I in the range that the plant's happy? Yes. Am I out of it? Okay, that's bad. Then we need to rectify that. But it is hard. And also traditionally making the measurement has been hard. Yeah. There's not been great tools for making these measurements, and that's been one of the things that we've continued to strive
until
to
the
do
TEROS-21
better.
and TEROS-22.
That's right, and so that's been the other reason that it's been a limitation, is just the inaccessibility of good measurements, and so hopefully, and I think we're seeing this, is that more people, now that the measurements are becoming more accessible, are starting to adopt that as a way to do irrigation management and better understand what the plant is feeling, rather than, that, I don't want to say guessing game, because it's an educated guess of what your water content means in terms of
water content is still really helpful. It moves the entire effort forward. But accounting for that soil type is always a challenge.
Yeah. Okay, we're coming to the end of our time, so this is going to be our last question. This one is asking, how does soil water potential influence hydraulic conductivity and water flow dynamics within the vadose zone?
That is a great question. And we all know that water potential is the driving factor in water movement because water is going to move from high water potentials to low water potentials because it's trying to come into equilibrium, and so it's going to pull water into those areas. Now, having said that, water potential doesn't really influence hydraulic conductivity, except for the fact that we know that in unsaturated conditions, hydraulic conductivity changes as the soil becomes, as the water potential decreases, because there's just that relationship. We know there's an unsaturated hydraulic conductivity curve, and we can derive that relationship, and we can measure that relationship between the two, but it's not influencing hydraulic conductivity in terms of like how the soil structure or the makeup of the soil is actually
more we're
influencing
looking at the change in soil flux based off of soil water flux based off of the gradient of matrix potential.
Right. But it's absolutely like if somebody's doing vadose zone hydrology and trying to understand water movement in unsaturated conditions, they need to know water potential and what that gradient is to really be able to quantify how water is going to move and how fast it's going to move, because that relationship is what's driving the movement. And so those two go hand in hand. We need to know the unsaturated hydraulic conductivity at those given water potentials.
Does it make a big difference that in saturated hydraulic conductivity that the gravitational potential is what's basically driving it rather than a tension?
And that's the thing about when you go from unsaturated to saturated conditions is your mechanisms that are driving movement shift completely. And also when you get to saturated conditions, you're typically dealing with the entire amount of the soil to move water, whereas in unsaturated conditions, as it gets drier, it's localized. The smaller pores are contributing more than the bigger pores, because the bigger pores, there's no water left. So as you drain those pores, the amount of soil that's actually contributing to the movement of water decreases. And so it is, it's a really interesting process to understand.
Is that the main difference between the saturated hydraulic conductivity and the unsaturated is the pore sizes that are engaged in transport?
Yeah, because those pore sizes that are engaged in transport shift, you move from where gravity's driving it to where it's actually the gradient in matrix potential that's driving it. So because that at some point gravity plays absolutely no role in the movement of water in unsaturated conditions.
And then your actual path gets longer and longer as your soil gets dry.
Longer and longer and more tortuous because you're dealing with less pores that aren't connected and all these types of crazy things.
Tortuosity, time.
That wraps it up for us. Thank you again for joining us today. We hope you enjoyed the discussion, and thanks again for all the great questions. And also, again, if you have any questions we didn't answer, please contact us via our website, metergroup.com. Finally, you can subscribe to the Meter Group YouTube channel and accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. Thanks again, stay safe, and have a great day.